Good evening, everyone. In this video, we'll continue with our discussion with system design decisions. We'll be looking at common architectural styles. There are several prototypical architectural styles that are very common in existing systems. Okay, so I'll be quickly mentioning about these things, and then we'll be discussing about them in detail in the coming slides. Okay, uh, more or less, this list is not complete. Okay, so these are some of the important ones. Okay, so most important prototypical architectural styles. The first one is the batch transformation. Okay, this actually deals with the data transmission executed once on an entire input data set. Okay, what it is, how it is used, we'll talk later. Okay, so then comes the continuous data transformation. Continuous transformation. So that a data transformation actually performed continuously as the input changes. Okay, the batch transformation. So there will be input, you will be doing some transformation, and you will get an output. Whereas a continuous transformation is something like approximately similar. The architectural style is approximately similar, but the point is like the input is regularly changing, so the output regularly changes. Okay, that's about continuous transformation. Then the interactive interface, okay. So the third type of architecture, a system basically dominated by external interactions, how you will be actually interacting with the system that will actually decide the architectural style for that one. And then like dynamic simulation, a system that simulates evolving real-time objects, okay. And then like the real-time system, a system dominated by strict timing constraints, okay. You need to get the response immediately, okay, and within certain point or something like that, okay. We'll see them. And the last one is the transaction manager. Okay, so a system concerned with storing and updating the data. Okay. Let us look at each and every type of the system. What are the architectural styles for those things? First, let us look at batch transformation. This actually performs sequential computations. Okay, so the application receives the input, and the goal is to compute an answer. Okay, that's from the beginning till end. So as this computation is actually happening, it is not interacting with the outside world. So you were given an input, you are doing certain processing, okay, and then like whatever the application does, like it is trying to generate the answer out of it. Okay. Some of the well-known examples are like compilers. Say for example, you give a code, and then like you will basically compile, and then like the machine code is to be generated. Okay, if it is Java, you basically give it, and then like you are basically getting the bytecode out of it. Similarly, like payroll processing, okay, so you do the processing continuously from end to end. Stress analysis of a bridge, okay, you give the bridge, architecture, everything, and you are doing the stress analysis of it, okay. So basically, like there is certain input given, and you are actually expecting an answer out of it. In such sort of systems, okay, so basically, like class model is very important. There are class models for the input and output for each and every intervening stages, so you can actually go across several stages. In this sort of system, like basically the interaction model documents the computation and couples the class model. Okay, so interaction model is also critical here. The most important aspect in such batch transformation is actually to define a clean series of steps actually. So these stages should be made clear. Okay. Let's look at an example. Here is an example for sequence of steps for a compiler. Okay, so this is a certain type of compiler where like you will give some sort of text in ASCII format in ASCII file. Eventually, the goal you are trying to come out is like you want to generate a database code. So that means like you will give certain text, okay, in a text file. Ultimately, it basically generates the database code so that like you can actually interact with the database. That is the task of this particular compiler. So what are the steps there? So basically, like first it has to take the ASCII file. Okay. So again, a class model for that one, and then like you have to parse the text. Okay, that will generate the graphics model. Then you basically determine the connectivity. Okay, this is specific to that particular compiler. We don't really have to worry about what are the things inside and what it is doing. Okay, but generally, what we should be seeing is like after a particular process in a particular stage. Okay, so we are passing the text and we are generating this graphical model, graphics model, and then like we are determining the connectivity. Okay, in the next stage, that actually generates the connectivity model, and then like then that connectivity model you have to take from an abstract model and you have to convert to an OO model. that generates a class model for you. And then like you have to generate the DB code, which actually generates the database code for you. Okay. So this is a sort of a batch transformation sort of application you can think about. Okay, so this is a common architecture. Okay, architecture style actually. Okay, so the steps in designing a batch transformation are something like this. So first you have to break the overall transformations into several stages. So here we are developing, breaking them into several stages. Is it? So basically parse text is one stage, determine the connectivity is another stage. Okay. So we have to basically break the overall system into these stages, with each stage performing one part of the transformation. So the, into the complete transformation, okay, so there are several stages, each is doing some transformation. So the prepare the class model for the input, okay, so here is a class model for the input for each stage, okay, and also like the output, which actually makes like a class model for between each pair of successive stages also like you have it. Okay, so you basically have to prepare these class models. Each stage knows only about the models on either side of it. Okay, so basically like parsing the text knows only about ASCII and then like graphics model. Okay, like that. Expand each stage in turn until the operations are straightforward to implement. Okay, so you may actually like say for example expand this particular stage okay further until everything becomes clear. Okay, until the operations that are to be performed okay are straightforward. Okay, we may have to restructure this pipeline for specific optimization purposes as well. So this is batch transformation. So next comes the continuous transformation. Okay, in the continuous transformation, the outputs actually actively depend on the changing inputs. The inputs are regularly coming, okay, and the outputs are continuously being generated. So continuously it updates the outputs. Okay, continuous is a little bit carried word here. Okay, so you will basically do it in practice in discretely. Okay, say for example, after every input comes, you will be doing output. Okay, so in discrete steps, you will be doing that. Okay, so for example, like signal processing. Okay, windowing systems. So how you will actually show them. Okay, so the okay, uh, something like a graphics application. Say for example, like you have the graphic model, how you are actually displaying it on the screen. Okay, so that's also like a continuous transformation. So regularly, like the graphic model is changing, and continuously you are displaying it on the window system. Okay. So one way to implement such a continuous transformation is with a pipeline of functions. The same way like we have seen in the batch transformation. But the point here with continuous transformation is like continuously these transformations are happening. The input is changing regularly, so as the output. Okay. Say for example, let's go by the same graphics model for the Windows system. So you basically have the graphic model which has to be mapped. Okay, so map with the view space model, you will generate the view space model. Then you have to clip it to the window model. Okay, that would actually generate the window model. Then you will basically have this sort of offset which actually gets you the screen image. So once you have the graphic model, you have to have the screen image. Ultimately, you have to display it in the Windows system. And here you can actually see like it is the pipeline. Okay, so the same way like batch transformation, it is done only once, but the continuous transformation regularly this input is changing, that is actually affecting the output. So this type of architectural style, okay, so the steps in designing, okay, so of course, like as I said, like you need to have, we have to define a proper pipeline for that. Okay, so we have to design a proper pipeline for that. So the steps in designing such a pipeline for continuous transformation are as follows. First, break the overall transformation into several stages, just like the way like we have done for the batch transformation. Okay, with each stage performing one part of the transformation. Prepare class models for the input, output, okay, and between each pair of successive stages. So these two are perfectly the same for both things. Then basically you have to differentiate each operation to obtain incremental changes to each stage. Okay, say for example, like every time like there are incremental changes coming. So that means like if it is a batch transformation, it is like complete processing you are doing. But then like say for example, for optimization sake, you are not doing the complete transformation or operation every time. But then like you are basically having incremental changes. An object moving something like this one, you don't want to completely render like this. Probably like you want to move, okay, or rotate or something. Okay. So of course, like for doing these sort of optimizations, you may have to add additional intermediate objects. Okay, that is also has to be taken care of. That's about this sort of continuous transformation. The next type of architectural style is these interactive interfaces. These are actually dominated by the interactions between the system and the external agent. So the ATM system, like say for example with the physical ATM, you are trying to regularly interact with it. Okay, the agents in this case can be like humans or like other devices. Okay, so basically it is dominated by the interactions between the system and the external agents. So examples are like form-based query interfaces, workstation windowing system, etc., with which like you are actually a desktop application with which you are actually interacting. Okay, so it's always interactive system. So the major concerns here actually deal with communication protocols. So the communication protocol between the system and the external agent, how they are actually communicating, what is the protocol which they are following. The system, the syntax of possible interactions. Okay, so for example, if it is a window-based system, like whether I can use, say for example, a mouse or like say for example a keyboard. Okay, possible interactions and what sort of interactions, the syntax of them. The presentation of an output, how you will present it, the appearance on the screen, whether you will put it everywhere or like whether you will put it in a particular place. Okay, and the flow of control within the system. Okay, and then like we are also worried about the performance, error handling, etc. We talked about all these things in the other design decisions. Okay, the same things like you have to consider for this sort of interactive interface as well, especially for the performance and error handling. We already looked at specific cases with the ATM, which is actually an interactive system in that sense. So the steps in designing an interactive interface are something like this one. First, you have to isolate the interface classes from the application classes. Okay, so in the application analysis, you already have identified the application classes. Okay, now this with this sort of interactive interfaces, you will have further classes like interface classes. We have to isolate them. Okay, and we may have to use to the extent possible, like use predefined classes to interact with external agents. Say for example, use predefined windows, menus, buttons, forms, etc. Don't build everything from scratch. It is again a form of reuse. Okay, so then the next one is like use the state model as a structure of the program. Okay, interactive interfaces are best implemented using, say, for example, this concurrent control. Okay, for example, using multitasking or event-driven control. When certain thing is happening, then you are actually dealing with it. An event is generated based on that one. We have discussed both the things in the controls. Okay, so in one of the design decisions. Okay, then with this interactive interface, we should be able to isolate these physical events from the logical events. Okay, a logical event corresponds to multiple physical events in general. Say, for example, like an interaction with the system means like a graphical interface can take input from a form. You put some information into a form, you click the menu. Okay, so you use the keyboard, etc. So all these are like these are physical events. One logical event is once the form is filled, and then like you are basically trying to interact. Okay, so that differentiation you should be able to get. You should be able to isolate both the things. So we have to fully specify the application functions that are invoked by the interface. By the time we are actually coming to this interactive interface, all these sort of applications are already well thought of. Okay, and we should be able to fully specify the application functions. Okay. So if anything is not ready, then we may have to go back to the design and analysis and design, and the other way. Then comes the dynamic simulation. These things actually model or track like real-time objects. Okay. Say for example, like molecular motion modeling. Okay. Say for example, in a chemical analysis, like how these molecules are actually moving, or like spacecraft trajectory computation. Okay. So for example, a spacecraft have to go out of Earth. So how you will be actually okay reaching that. Okay. So that velocity. Okay. So how you will actually model and how you will actually simulate those things, and economic models, etc. The objects and operations come directly from the application. Okay, so that is a clear point we should remember. The objects and operations come directly from the application. There are two ways of implementing such a control. Okay, one is like we can have an explicit external controller, okay, to the objects, okay, to the application objects, okay, and this can actually simulate a state machine. So how the objects are actually communicating, etc. Okay, so there can be an external controller for that one. Alternatively, the objects can themselves actually can exchange messages. Okay, similar to the real world situation. Right? In the real world situation, the physical objects are the ones which are actually exchanging messages. There is nothing else which is actually controlled. Okay. Philosophically, I think there can be different models for it, but in general, like these physical objects are actually communicating. Okay. So the objects can exchange messages themselves. So in that way, like in these two ways, like we can actually implement a control. Okay. So there is an external control, which is actually controller, which is actually managing all the objects in some form of state machine, or like the objects are communicating among themselves directly. So when we think in terms of this sort of dynamic simulation, unlike an interactive system, the internal objects in a dynamic simulation do correspond to real objects. Okay, so within a simulation thing, like the objects which you have created actually map to the real world objects. So in that sense, like class model is very critical here. Okay. At the same time, like since all the things are actually interacting, okay, so these real world objects are like these simulation objects are actually communicating among themselves. They are interacting, okay, they are passing messages or whatever it is. So similar to an interactive model, the state model and interaction models are also important here. Okay, this is a type of application for which like all the models, okay, class model, interaction model, state model, and interaction model, all three models are actually critical. The steps in designing this sort of dynamic simulation are something like this. We have to first identify the active real world objects from the class model that I have been talking about. So you have to identify these real world objects. Okay. And then like we should be actually identify the discrete events. So the discrete events with the objects, how these objects, okay, discrete interactions, how you are trying to interact with that particular object. Say for example, turning power on or applying a brake, okay, on a particular object, to a car, okay, something like that. These discrete events can actually be implemented as operations on the object. This we have actually discussed as well earlier. Okay, so these discrete events can be implemented as operations, okay, on the object. Then we have to basically identify the continuous dependencies. Real world attributes may be dependent on other real world attributes, okay, or vary continuously with time. Say for example, something like, okay, so they are dependent on other real world attributes, like they may depend on time, velocity, okay, so different types of real world attributes, okay. And then like the generally simulation is actually driven by a timing loop at a fine time scale. So if it is discrete event simulation, like discrete every, say for example, few milliseconds, like you are doing a simulation, okay. So like that, it is a discrete steps. Okay. That's about dynamic simulation, okay, type of architecture type. Then comes the real-time systems. This is an interactive system with tight time constraints on actions, okay. So, for example, like video conference applications, okay, so continuously like the response and so it has to happen, okay, so video conferencing application. So the video is actually streamed, okay, so the other person is responding and you are also communicating. So it is real time application. There can't be any breaks, okay. Say for example, like whatever the thing which I am talking now is relevant exactly at this moment, okay. It is not like, say for example, after 2 or 3 minutes if we send that thing, it will not lead to any proper communication, okay. So these are the sort of interactive systems we are talking about in terms of real-time system are concerned. There are hard real-time software, okay. These things actually involve critical applications, require a guaranteed response within the time constraint, way like I have given you, okay. But then there can also be like some soft real times, okay, that must, I mean, like they also should be highly reliable, but can occasionally violate time constraints. Okay, say for example, like, I mean, let's take the same video conference application. So occasionally, if I miss a frame or something, like it will not be a serious issue. But at the same time, like say for example, think about a real-time system, like where in a factory setting, okay, so if something happens, immediately an alarm has to be raised. Okay, so for example, a fire is happening, immediately an alarm has to be raised. Okay, so that's a real-time system. It cannot, like, say for example, after the fire happened, like after some 15 minutes, like it is raising the alarm, then it is not functioning properly. Okay, so these are all come into hard real-time softwares basically. The other type of applications, of course, I already have given you the example, video conferencing, this industry applications. Okay, so we can also think about device controls, online gaming again. Okay, so these are all real-time systems. Designing real-time systems is a little bit complex thing. Okay, so I mean, like it cannot be just explained in these sort of 4 or 5 steps, or like what is relevant. Uh, they are very complex. Okay, and they actually involve several issues such as interrupt handling, prioritization of tasks which tasks have higher priority, coordinating across multiple CPS. Okay, so these sort of architectural style design, the steps will be like pretty huge. Okay, so just to know like if these type of systems are also possible is already sufficient to have the basic architectures. That's about the real-time system. Then the next one is the transaction manager. The transaction manager is a system whose main function is to store and retrieve data. Okay. Primarily, like, these things actually deal with multiple users who actually read and write data concurrently. It is almost like a database management system actually. So transaction managers are often built on top of a database management system. Okay. So regularly, like say for example, a database management system, say for example, it can write something, okay, and then like okay, read something and then like make some modifications, etc. But the transaction manager actually say has to see like okay, so multiple users can basically read and write this data concurrently to that particular DBMS. Okay, and it must also secure all the data. Okay, and it has to take care of all this concurrency and everything. So in these particular type of systems, okay, so the architecture style, the class model is actually very dominant. The state model is occasionally important, especially for specifying the evolution of the objects as well as constraints and methods that actually apply at different points in time. Okay, so state model is also occasionally important, but the interaction model is not so important. Okay, so for this particular type of applications, for these particular architectural styles. So the steps in designing an information system, okay, so especially in this sort of transaction manager or something like this. So we must first map the class model to the database structures, okay. So that's what you are actually doing. Then you have to determine the units of concurrency, the resources that inherently or by specification cannot be shared. Say for example, like while you are making a modification, you cannot actually uh, make another read or something. Okay, so basically like the unit of transaction is something like this one. Okay, so the set of resources that must be accessed together during a transaction. Okay, so basically like a transaction may involve like okay, so get the user details. Okay, so change his uh, uh, say for example salary and then like update it. Okay, update the salary. Okay, and then like commit. This is all becomes like a single transaction. So a transaction as a whole like succeeds or fails. Say for example, if there are two users in a banking system, okay. So if you are trying to add money to one person, like you are actually withdrawing money from another account, okay. So account by account transfer. So one account basically gets plus, another account basically gets the minus, okay. So you are deducting from that one, you are actually adding it. This all becomes like a single transaction. It cannot fail in the middle. If it fails completely. Okay, so it basically reverts back. Okay, so the money is coming back. So it says like transaction failed. The transaction manager has to actually take care of that one. Okay, and then like if it really wants, like it has to continue the thing, try it again. So design concurrency control for transactions. The system may need to retry failed transactions several times before actually giving up. Okay, that's what I was talking about. So if you want to start a transaction, either it succeeds fully or like it fails. If it fails, like try several times. Okay, this is the sort of designs you should be considering. Okay, when the architectural style is of the type transaction managers. So we have looked at all the 6 different architectural styles. Okay, so there are several others. Okay, as a set which to study about the things, it is already sufficient. Now let us look at the complete actual architecture of the ATM system. The ATM system architecture we already have seen. So basically like there are several ATMs existing and then like there is this consortium computer. Okay. and then there are several banks. Okay, so in that sense, the architecture of this ATM system, this is an hybrid of interactive interface, because like with the ATM you are actually interacting, and a transaction management system actually. So the entry stations at the ATM are actually interactive interfaces with which like you are actually putting certain information, putting your card, and then like trying to see the data or doing some transactions. The consortium and banks are primarily a distributed transaction management system. Okay, so in the background. So in terms of the processing is concerned, the ATM system actually processes each transaction as a single batch operation. Okay, so while it is actually doing that particular transaction, okay, so each transaction, it is actually locking that particular account until the transaction is complete. Okay, so that means it is actually doing some sort of this sort of batch operation. Okay, in that sense. Okay, again, like it is basically dealing with the transactions also for that particular case. Okay, so it is basically a hybrid model of these several architectures which we have discussed, because the ATM itself has multiple subsystems. Again, like even concurrency also arises, and it is also critical here because there are several ATM stations. We have discussed that in detail. How you will be actually be able to support multiple requests. Okay, and the point which actually will be seriously affected by this one will be the consorting computer actually. Okay. In terms of the controls are concerned, the consortium computer and bank computers will be event driven. When a certain event is happening, okay, so then they are doing a certain transaction. The user is basically initiating certain transaction, so they are actually implementing the transaction. And of course, like we talked about several design decisions. Okay, so for ATM as well, like there are several design decisions which should be considered. It should be fast and all sorts of things, and it is a financial system. It should be fail safe. Transactions are of the highest priority here. Okay, that's about the ATM system, and then in general, all the design decisions which you should be taking. Okay, so we have discussed all the things in detail. So with this one, we finish the discussion of chapter 14. Okay, so of this object-oriented modeling and design with UML. Michael Blaha and James Rumbaugh. Thank you very much for your attention.